Okay, so today we'll start to switch gear completely. So we'll move from the proof of the theorem to applications of the theorem. So this is the part where we will see most of the connections to extremal combinatorics. So let me just first sketch out what is roughly the high-level connection here. So lots of results in extremal combinatorics would have the following form. If you have graph G that has a sufficiently high minimum degree, at least some function of the number of vertices n in the graph, then one can guarantee that G contains some specific target H as a subgraph. Now, for the beginning part of the mini course, as we saw, one of the motivating question was, well, if we fix H as any graph on n vertices, what is the probability that the random graph G and P contains H as a subgraph? So to make the connection clearer to this theme in extremal combinatorics, the question that we will ask will be along that line, but just a little bit more general. So this is usually what we want to go for. Let's say we have some extremal results, guarantee some worst case minimum degree condition under which we can always guarantee a copy of H as a subgraph. Now we want to say that under the same condition, even if we sparsify the graph G by, then let me write this one and then I'll explain what it means. So I start from the graph G, which at least is guaranteed to contain a copy of H. Now I will define here this random subgraph GP of G and it is simply obtained by just retaining each edge of G independently with probability P. So of course, we can make the very simple observation that this kind of question at least generalizes the questions that we considered earlier, which just ask about the random graph G and P. And the reason is simply because if we take G to be the complete graph Kn, then this random subgraph GP is exactly the Kadish-Renyi random graph G and P. And in fact, for many of the results along this line that we will see, we'll make the observation that, well, when in the case when G is a complete graph, so in the case of the random graph G and P, we define the threshold P, that's the value at which we can guarantee that the random graph G and P typically contains a copy of the graph H. Well, we usually are interested in results of the form, even if we don't start from the complete graph, as long as we start from a graph G with the same minimum degree condition as in the extremal combinatorics result, guaranteeing to us that, at least in the worst case, this deterministic graph G contains a copy of the graph H, then even if we sparsify G by some probability that is on the same order as the threshold of H in G and P, this random subgraph GP will still typically contains H as a subgraph. So this is kind of the reason why it's called robust threshold. So we are trying to say that this condition, which guarantees even just a single copy of H, in fact guarantees somehow that H will have to robustly appear in the graph G, and it appears even if we sparsify G by something that is on the same order as the threshold of the graph H in a random graph G. Okay, there's actually the third setup that we will also briefly discuss. So this is the perturbed random graph model. This was introduced by Bowman, Fries, and Martin. So in this model, well, we'll try to ask the following question. So let's let G be a graph with some minimum degree condition. Let's say at least some constant fraction, alpha times n. Now we ask, okay, now we construct a random graph G bar. So let's let G bar be the union of G and some additionally random graph G and P sitting on the same vertex. Okay, so here we will now ask for what value of P does G bar typically contain a copy of H. So in this setting, of course, if G was the empty graph, so if alpha is equal to 0, then G bar is just the additionally random graph. So there we know that the value of P that we need to take is the threshold of the family of copies of H on n vertices in this random graph G and P. So here we are asking, well, if we are now given in advance the advantage, which is just an arbitrary graph, deterministic graph G with some minimum degree condition, can we actually guarantee that even if we include some random graph G and P, where P is much smaller than the threshold of H, we can still guarantee that this union of the high minimum degree graph and this random graph will contain a copy of H. So these are roughly the broad general setup for the question we will study. So maybe let me first state how things would look in one motivating example. So the first example, let's consider the graph H, which is the Hamiltonian cycle. Okay, so in this case, well, the first thing which we already mentioned early on is, okay, again, I'll use script H for the family of all copies of H on n vertices. So the threshold for this family, so how large does P have to be so that G and P typically contains a Hamiltonian cycle? As we mentioned before, this is on order log n over n. And this, so this goes back to classical result of Posa in the 70s. Now, what is the corresponding extremal combinatorics result? This is, of course, just the classical Dirac condition or Dirac theorem. So Dirac tells us that if G has minimum degree at least n over 2, then G contains a Hamiltonian cycle. Okay, and so this is also, as we know, a tight condition, right? So we cannot put, so we can construct a graph with minimum degree n over 2 minus 1, and it will not, and such that it does not contain a Hamiltonian cycle. So let's now consider the corresponding results for the Hamiltonian cycle in this robust threshold setting, in the perturbed random graph setting. So in the robust threshold setting, we have the result of Grigorovich, Lee, and Sudakov. And they show that if G has the same minimum degree condition as the Dirac condition, then actually, even if you sparsify the graph G, by the probability, which is on the same order as the threshold PC, so C log n over n, this will still contain a copy of the Hamiltonian cycle with high probability. That's the robust threshold result. Now let's say what is the corresponding result for the perturbed random graph model. So in this case, we have the result of Bowman, Rees, and Martin. And they prove that, well, if the minimum degree of this graph G is already at least 1/2 n, then there's nothing we need to do, right? Because already G by itself contains H, so there's no random graph that you need to put into the picture. So let's consider some constant alpha that's between 0 and 1/2. Now, if G is a graph with minimum degree at least alpha n, then G bar, which is the union of G and a random graph Gn, constant over n. This would already contain a Hamiltonian cycle with high probability. So we see that as long as alpha is strictly bigger than 0, we will have a separation from the perturbed random graph and just the Edish-Rényi random graph. So in particular, in the Edish-Rényi random graphs, in the case when alpha is equal to 0, we may need to take this probability to be at least constant log n over n in order to guarantee a copy of the Hamiltonian cycle. But as long as we have any positive fraction, alpha, guaranteeing a minimum degree, then we can drop this log factor, and it's sufficient to just take a random graph with probability C over n. And in fact, this is tight. And the example which you can consider is to take the graph G, that is an unbalanced bipartite graph. You choose the two sides so that it has minimum degree alpha n. And in this unbalanced bipartite graph, you can observe that you need to add at least a linear in n number of edges in order to find a Hamiltonian cycle. So we need at least here something like C over n. There's actually one final result, which I didn't say it over there, but actually is also related to all of these. So the last result is a counting result. So the deterministic condition tells us that, well, when delta passes some threshold, we can guarantee that we find at least one copy of the graph H. But actually, what tends to happen, and in particular in this Hamiltonian cycle case, is that as soon as the minimum degree of the graph is at least n over 2, we will not only find one Hamiltonian cycle in the graph, but we'll actually be forced to find many copies of the Hamiltonian cycle. Okay, so we will be able to say that G contains at least some constant times n to the n, many Hamiltonian cycles, many copies of it. So this is a result of Sarkozy, Selko, and Zemeredy. And then this constant is even determined exactly in the work of Kepler and Kahn. Okay, so almost that as soon as we let the minimum degree cross this critical threshold of n over 2, we'll jump immediately from potentially having 0 Hamiltonian cycle to having this, well, obviously nearly maximal number, this constant n to the n, many Hamiltonian cycle. Okay, so so now what I will do is to give you the similar parallel, like the story here for the Hamiltonian cycle, but for a lot of the more complicated combinatorial structures, and overstate just the whole set of results to give you the picture, and then we'll discuss the technique today, and then we'll zoom into some of these applications more tomorrow. Okay, so now let me. Okay, how we raise it. So as I said, there are lots of results in extremal combinatorics of the form like Dirac's theorem. So for other more complicated structures, so for instance, we have this theorem of Corradi and Heino. That tells us that if the minimum degree is at least 2n/3, then G contains a triangle factor. So here, triangle factor is simply a collection of vertex disjoint triangles in a graph G that covers all of the vertices of the graph. So in particular, here we are assuming implicitly that n is a multiple of 3. Okay, and then Heino and Zemeredy generalize this result to logic fields. So he shows that if they show that if the graph G is at least k over k plus 1n, then G contains k plus 1 factor. Now, there's another way actually to rephrase this theorem of Heino and Zemeredy, which is actually sometimes very useful. So you can rephrase this theorem as saying that if we have a graph with maximum degree delta, or if we have a graph with maximum degree delta, we know that we can color the graph using delta, maybe delta plus 1, many colors. And this theorem will guarantee that we can actually color the graph so that the color classes have equal sign, have nearly equal sign. Okay. So let me write over here the parallel results in the probabilistic setups. This theorem of Corradi and Heino, the robust version was obtained by okay, so Alan Butcher, Austin Davies, Jensen, Morris, Roberts, spoken. Maybe 2023, some quite recently, and they show exactly the robust generalization of the Corradi-Heino theorem. So if under the same condition, if the minimum degree is at least 2n/3, then even if we sparsify the graph G, and the probability of sparsification is this quantity here, log n to the 1/3 and to the negative 2/3, then it still contains a triangle factor with high probability. So, well, what's the significance of this? This is actually exactly the threshold for a triangle factor in an Edish-Renyi random graph. Okay, so we're saying that even if we don't start from the complete graph, we can sparsify at the same level that we are allowed to in a complete graph, and we can still guarantee that the random subgraph will contain a triangle factor, as long as we have this minimum degree condition. So originally, they proved this theorem by developing the technique of behind the seminal work of Johansson, Kahn, and Wu. And in particular, it's very beautiful, but at the same time, very difficult. And then in joint work with Ashwin Sarvitafani and Michael Simkin, around the same time, but after this work, we show, well, first we gave a very short proof of this theorem, proceeding through construction of an appropriate threat measure and then using the Kahn-Kalai conjecture. But we can also quite directly generalize the result to larger clique factors. So if the minimum degree is at least k over k plus 1 times n, then even when we sparsify the graph by the threshold of the clique factor in the random graph, which will be some constant times log n to the 1 over k plus 1 choose 2 n to the negative 2 over k plus 1, it will still contain a k plus 1 factor. And as a direct byproduct of the construction of the spread measure, we also obtain that if delta of g, again, is at least k over k plus 1 times n, then g contains at least the right number of k plus 1 factor, which is some constant times n to the kn over k plus 1. K. Yes. So yeah, originally they observed that as a corollary of this threshold result, one will be able to obtain a counting result for triangle factors, but losing a log factor inside here. So instead of constant n, we'll lose some log factors. And as a byproduct of our proof, we can actually recover the sharp count without the log factor loss. Now, both of these results are actually instances of a general family of results that you can consider. So let me define, for example, this Dirac threshold in the general hypergraph. So the setup here, if we have a k-uniform hypergraph, and then we fix some parameter L that is at most k minus 1. Then we can define this parameter delta Lk. This is roughly the minimum L2 degree condition that will allow us to guarantee that the hypergraph contains a perfect matching, for instance. So right, this is a limit. Quantity T n KL over normalized by n choose k minus L. T n KL is the minimum D such that every hypergraph H with L2 degree, minimum L2 degree at least B, contains, let's say, a perfect matching. So in general, we don't know, apart from very specific cases, what these parameters delta Lk are, but we do know that this limit exists. And so let's say that we denote the correct answer to this extremal combinatorics problem by this parameter delta Lk. Then in general, we can upgrade the extremal combinatorics result to the corresponding robust threshold setup. So this we proved in our work, but also was shown by Dong-Yat Kahn, Kelly, Holtzman, and Fenninger at the same time. That if you have the same, or at least maybe a tiny bit of a slack above this required minimum degree condition, so if the L2 minimum degree of H is at least this parameter delta Lk plus some epsilon times n choose k minus L, then even if we sparsify H by the optimal order, which is constant log n to the 1 minus k, if you remember, this is the threshold for the Edish-Renyi random hypergraph to contain a k-uniform perfect matching. And we can specify by the same order up to a constant and still guarantee that this contains a perfect matching. Okay. Update some more results with this flavor. So for instance, we have yes. Yeah, we can also give the counting results. So actually for all of our applications as a byproduct of the argument which we produce is optimally spread measure, we also get the correct for the objects. We'll see a little bit more into the way we prove it later, which will hopefully clarify it. So now we have lots of theorem of Kamlosh, Sarkozy, and Zemeredi. They were all applications of the regularity method and the Blow-up lemma, together with, of course, a lot of works and insights. And these guarantee minimum degree conditions under which we can find specific spanning graphs in a graph G. So the first result I will state is the resolution of Bolobash conjecture on the minimum degree condition for a spanning tree. If the minimum degree of G is at least half plus a little bit times n, and here we do need that little bit, then G contains a copy of any bounded degree spanning tree T. So over here, we can upgrade this to the robust threshold version. So if delta of G is at least half plus epsilon n, then even if we specify G by order constant log n over n, this will still contain T with high probability. Now, play the last result, and then I'll move to at least one result on the perturbed random graph setup. For this last one, we have again a theorem of Sarkozy, Kamlosh, Sarkozy, and Zemeredi. Now it is the resolution of a conjecture of Coulthard and Seymour. So they show that if minimum degree of G is at least 1 minus 1 over k plus 1 times n, then G contains the kth power of the Hamiltonian cycle. So again, let's just draw the 2 power of the Hamiltonian cycle. You have the usual Hamiltonian cycle, and you also add in edges between every pair of vertices that are at distance at most 2 on the cycle. And okay, so if you want the robust threshold result, at least if you allow some slack in this minimum degree condition, then we'll see as a byproduct of what we discussed that this is not very hard to get. If delta of G is a bit bigger than this critical minimum degree, then even if we sparsify G by the correct probability, which is a constant times n to the minus 1 over k, for k at least 2, okay, this will still contain the kth power of the cycle, the Hamiltonian. So this is for k at least 2. That's when we know that the threshold in the Edish-Renyi random graph is of order n to the minus 1/2. In particular, there's no log factor needed. The expectation threshold is the same. It's also order n to the minus 1 over k. For k equals to 1, we will need, well, we are actually saw that result before, the Hamiltonian cycle. In that case, we will need the additional log n factor.
So the same, the statement maybe depend on the
Yes. Right. The C in the statement depends on the epsilon. But for a lot of problems, so we'll see that what we do is quite literally, we take the proof of the extremal combinatorial result and then try to upgrade it to the threshold probabilistic version. And in many cases, in order to obtain the exact correct minimum degree threshold, what we need to do in order to prove this theorem is, well, we will apply the regularity method, which will come with some of these small annoying epsilon and kind of bad vertex sets. And one will need to then zoom in closely in kind of the extremal cases, identify the extremal cases, and then do careful stability analysis in order to remove the need for this additional epsilon. I'll not, at least definitely in this and tomorrow lecture, I'll not get to the hairy details of the application of the regularity method, especially for removing the epsilon. So I'll just state this version here. Okay. But yeah, if one works hard enough, this one should in principle be able to remove the epsilon. That would require still some time. So, right, so far, still no result for the perturbed random graph model. So let me state some results for the perturbed random graph model. We saw actually one for the Hamiltonian cycle. It turns out that for the powers of the Hamiltonian cycle, we see actually some fairly interesting phenomenon. So let me just draw here what happens for the square of the Hamiltonian cycle in the perturbed random graph model. So here, we know that if we have minimum degree at least 2/3, then the graph with minimum degree 2/3 already contains a square of a Hamiltonian cycle. So obviously, we do not need any further edge from the random graph. So let's consider now this minimum degree alpha, which is less than 2/3. So it turns out what happens is for alpha between 1/2 and 2/3, the number of edges, the density of the random graph that you need to throw in additional to this graph with minimum degree at least half n, is of order 1/n. So here you need to throw in something like Gn constant over n, and that's actually enough to give you a copy of the square of a Hamiltonian cycle. Now, for every integer k, you have some interesting transition whenever you hit 1/k. So what are the answer in these ranges? So in between 1/k and 1/k plus 1, the answer is some constant n to the negative k minus 1 over 2k minus 3. And exactly at 1/k plus 1, you will need the log factor. So you get exactly the same answer with a log n rational power. Yeah. So in this full picture, so this is a full picture, and right. This we know, and it comes from several different very nice works. And my apologies, I forgot to write down the reference here. So I'm missing the reference for this nice picture that we know for the square of a Hamiltonian cycle. But in particular, for this perturbed random graph model, we do know kind of entirely all that we want to know for the square of a Hamiltonian cycle. And one of the main reasons why the square of the Hamiltonian cycle is a good case to get the complete picture is that the square of a Hamiltonian cycle is kind of the limit under which we can kind of build the square of a Hamiltonian cycle by, in this perturbed random graph model, by piecing together a few different large but constant size pieces together. And if you want to then move to the third power and beyond, it would not be possible to do that. And so we will need some different technique to address the bigger cycles. And here I'll just take an example of some results that we know for the third cycle. I believe that we can, in principle, uncover a lot more about this picture. So with right coordinates, we prove that for k at least 3, so the third cycles and beyond. And we were interested in this specific range of the minimum degree. Delta of G is at least 1 over k plus 1 plus epsilon times n. We can guarantee that G together with a random graph with probability constant n to the minus 1 over k minus 1. Then this will contain the k power of a cycle. So I'll show you a sketch of this result maybe tomorrow. Let's just see. Okay, this is tight up to the constant, and what is epsilon is potentially not tight. Again, one would likely need to do the careful stability analysis on top of the regularity lemma. And usually the insights one can go back to the proof of Combinatorics and Zemeredi, but one would then need to kind of read into the details carefully and then redevelop their main ideas. But usually it's some translation that could be done. Now, ignoring this epsilon, this result is tight. And what is very suggestive of this threshold, n to the minus 1 over k minus 1, is that this is actually the same as the threshold for the random graph to contain a k minus 1 power of the Hamiltonian cycle. Okay, and to build directly a second power of a Hamiltonian cycle in a random graph is kind of the first case where we cannot just piece together different small size pieces. So if you want to build a path, then that is kind of easier. For the square of a Hamiltonian cycle, that becomes hard. And that is why usually in this perturbed random graph results for building the powers of the cycle, what we will do is we will use the underlying graph with high minimum degree to build some structure that allow us to then say that in the random graph, we don't need to find the kth power of a cycle, but we only need to find something that's closer to a smaller power of the cycle. And that explains exactly this threshold here, but we'll see a lot more details of this. Okay, so with that, I mentioned that the results in extremal combinatorics, at least many of them, including all of the results of Combinatorics and Zemeredi, they are all applications of the regularity method and the blow-up lemma. So let me now turn to give you some quick introduction to the regularity method and the blow-up lemma. Then we will see how we can upgrade the classical extremal results in order to obtain the probabilistic results and a robust threshold for perturbed random graph.
Did you use the uniform measure for consulting the spread measure or?
No, so right. So very different from all of the previous cases that we have seen. In all of the simple cases, and really kind of the only cases where we know, apart from those which I'm going to tell you now, for which we know how to construct the optimal spread measure. In these cases, we can just take the uniform measure and then checking the spread property is some kind of trivial enumeration exercise. In these cases, because we start with a general graph G, we only have the minimum degree condition, but even in principle, the degrees in the graph can fluctuate by some constant factor. And in that case, you can actually see that you cannot pick the uniform measure and hope blindly that it will be a spread measure. So the measure we construct will not be the uniform measure, and it's constructed from some algorithmic procedure in order to kind of hard code in the spread property, but in general, we can't hope to use the uniform measures. Still, in many cases, even if we want to use a uniform measure under this type of condition, we don't really understand the uniform measure well enough to control the spread property. Okay, so quick problem to the regularity method. So let's start with the classical definition. So if I give you a graph, bipartite graph G, between two vertex sets A, B, and I'll call E the H set, we'll say that G is epsilon regular. The usual notion, if for every subset A prime of A, B prime of B, A prime has size at least epsilon A, B prime has size at least epsilon B, the edge density, I'll write first and then I'll define it, between A prime and B prime is within epsilon of the global edge density between A and B. Here, D of A prime, B prime is just the number of edges between these two vertices A prime, B prime, dividing by the products of the size of A prime and B prime. So, classical result in the regularity method is the regularity lemma, which is immensely powerful. And Semiramis' regularity lemma says that for every epsilon positive, there would exist some finite number depending only on epsilon, on an m of epsilon, such that every graph G, you can assume that G has a large enough number of vertices relative to epsilon to make things non-trivial, admits a vertex partition into, well, at most, m of epsilon parts, B1 up to Bm. Well, we can assume, okay, here we'll assume that they have roughly equal sign. So every two of these parts, Bi, Bj, the size can differ by at most 1. And we'll have the condition that all, but at most, epsilon m squared pairs of parts Vi, Bj are epsilon regular. So this is the classical, usual statement of Semiramis' regularity lemma. There are, of course, many different versions of Semiramis' regularity lemma that one can write down. And especially if one cares about the quantitative bound to m of epsilon. It will be very bad anyway, it's the tower type, but if we care about exactly the bound for the tower height, then we might have to look at some variants of this version right here, but for our usage, stick to the classical statement of the regularity lemma. So for us, we will need a little bit more than just epsilon regularity because we want to embed spanning structure, right? Even if we have an epsilon regular pair, there's no condition guaranteeing that every vertex in this graph have at least even just an edge going out of that vertex. We could have vertex of degree 0 in a graph that is epsilon regular, and that is of course not good for embedding spanning structure. So useful definition to make here is a strengthening of this notion of being epsilon regular. So we'll say that G, again, this bipartite graph, is epsilon delta superregular. Well, if first it is epsilon regular in the usual notion here, and furthermore, the minimum degree of G, so here, for convenience, let me now assume that the two vertex parts, A and B, they have the same size, which we write little n for the size of the parts. And here we will say that G is epsilon delta superregular. if beyond the epsilon regular property, we also have a lower bound on the minimum degree of this graph G. Okay. There is a stronger version of this, which will allow us to drop one parameter. So let me say that G is just epsilon superregular if, well, roughly it is epsilon delta superregular for delta being equal to the density of the graph G. So in other words, if G is epsilon regular with density D, and the minimum degree of G, or in fact, here for this notion of epsilon superregular, and every vertex of G has degree D plus minus epsilon times n. Okay, so in an epsilon regular graph with density D, it is easy to show that most vertices will have degree D plus minus epsilon times n. So this, I just mean the degree is between D minus epsilon times n and D plus epsilon times n. And I'll say that the graph is epsilon superregular if there's no vertex with the abnormal degree. Okay, so I want to state maybe one convenient lemma for turning any epsilon delta superregular graph into an epsilon superregular. So lemma. If we are given a bipartite graph G, which is epsilon delta superregular, then we can actually replace G by a spanning subgraph with the following nice property. So for on D bar, not too large, equals delta minus some big constant times epsilon. G contains a spanning subgraph. This is useful because we care about spanning structure, which is now epsilon prime superregular and it also has density exactly this parameter D bar. So here, this epsilon prime will still be small, will be something like root of epsilon. Okay, so in other words, in our later applications, if we have maybe a bunch of graphs, like a bipartite graph, where every pair is epsilon delta superregular for some epsilon and delta, then we can use this lemma to actually assume without loss of generality that we have a bipartite graph for which every pair is epsilon prime superregular for some small epsilon prime, and furthermore, all of the pairs have the same density. So we can always just assume that for free. So maybe just very sketch briefly the proof of this, the usual maneuvers with the regularity lemma. So here what we do is, okay, so let's let D be the density of the graph G that we start with. We know that in this bipartite graph G, because it's epsilon regular, there can actually only be small number of vertices with too small degree and small number of vertices with too high degree. Okay, so let's say that the vertex V is in this low degree part L if the degree in the graph G of the vertex V is smaller than D minus epsilon times n. Let me call this D naught so I don't confuse myself. Okay, similarly, you define the high degree vertices, and both of these sets are small. They have size at most big O of epsilon times n. So now, how will we obtain this spanning subgraph? G bar Well, okay, so what we will first do is the density of the graph G is D naught. This is potentially bigger than the target density D bar that we have. So we will let first actually D be something that is a tiny bit bigger than D bar. So let's say D bar plus some constant epsilon. And then we'll obtain first an intermediate graph G hat by sampling the edges of G with probability equal to D over D0. Okay, and our constraints guarantee that D over D0 is always at most 1. So after we do this, we can use just standard Chernoff bound to guarantee that this random subgraph G hat, it will actually inherit the epsilon regular property of the graph G that we start with. Maybe epsilon becomes a tiny bit bigger at 2 epsilon. But apart from that, it will still be an epsilon regular spanning subgraph of the graph G. Now, of course, what we can't immediately guarantee is information about the minimum degree. So what will we do now is for every vertex V in L, it has minimum degree delta n, which is much bigger than epsilon n. So it has lots of neighbor in this part lying outside the exceptional sets L and H in this other part. Okay, so for that vertex V, it has some degree in the graph G hat. We'll just add arbitrarily the neighbors, the edges in between V and the neighbors outside L and H here in order to get the vertex V to have the correct degree. Okay, so for V in L, we will add D times N minus the degree in G hat of V. Oh, yeah, actually, I went a bit maybe too fast. I should have defined. So 1 second. So let me, okay, what we should do is we first sample this random subgraph G hat of G, and we define L and H with respect to G hat. Okay, so this should not be D naught, this indeed D. So in G hat, we will add the correct number of edges we need to the vertex V that have too low degree. And similarly, for the vertices that have too high degree, we will remove edges, but we will only remove edges between this vertex and the typical vertex here. So after this step, we have been able to guarantee that every vertex in the graph will now have the correct degree. So in fact, we can show that we can, because there are many vertices in the typical part, and there are very few vertices that are exceptional, we can show that the modification that we do here will not affect the degree, at least will not affect more than an epsilon n factor, the degree of vertices in the typical part. So after this modification, all vertices in the graph will have the correct degree. And the graph is also epsilon regular. So this is now already super regular. The only thing that one needs to do is that the graph have density D, which is something that might be bigger than D bar, have density, well, it has some density that is at least D and close to D, but we don't know exactly what the density is. And if we want this statement, then we only need to do the last small change in order to guarantee that the graph have density exactly equal to D bar. But this is actually also easy because now in this super regular graph with density slightly above D bar, we can just actually greedily go over the vertices and remove around each vertex something like epsilon n many edges around it. We can do this process in such a way that we guarantee that none of the degrees are being pushed by more than epsilon from what it is currently. And after the end of that process, we will be able to guarantee that we have this epsilon prime super regular subgraph that has density exactly D bar. Okay, so what of a sketch, but the rest of the details are not very important for what we will do next. So let me not spell it all out. So So in particular,
That means the high degree part still have to delete some aggregate incident.
yeah, so we do the same thing. So for V and L, right, so we delete the right number of edges between V and the typical set, but there's lots of room, so there's nothing that can go here. So right. Okay, so we state here the regularity lemma because we care about the following result. That is also very powerful. This is a blow-up lemma. Of Tolosh, Kondi, and Semeredi. Okay, so now the result is somewhat long, so please bear with me as we state the result. We have some parameters here. So we have R, delta, delta, and then we will need to take some epsilon sufficiently small. So what does this result say? So first we have some graph R, like the reduced graph after you apply the regularity lemma. Let R be a graph on little r vertices. And as the input to the problem, we are given a graph G. G is actually a R-type graph. And the parts are V1 up to VR, say. Now, for every edge I in J, so I will identify the vertex set of this graph R with just the interval between 1 and R throughout. For every edge I in J in R, will force that the corresponding pair of parts in G, Vi, Vj, this has to be epsilon superregular. Or maybe if I'm less lazy, because I'll apply that result anyway, epsilon delta superregular for delta much bigger than epsilon. Then we are given this target graph H that we want to embed. So let H be a graph with a homomorphism little h from H to this graph R on R1. We'll need the constraint that the inverse image of any vertex of R will have size at most the size of Vi, but in fact, let's assume even without a lot of generality that it has size exactly equal to Vi. Then we also need that the max degree of H is bounded. Okay, the conclusion is that G contains a copy of H. Okay, this is a little bit hard to parse. What is this saying in word? Oh, sorry, in a picture. So here we have an R-partite graph. Let's just say R is equal to 3. And we are given here some R-partite graph G for which across the correct pairs, we have some superregular bipartite graph. Now we have a target graph H, and really the only constraint that we have on H here is that it is some bounded degree subgraph of the complete tripartite graph between these three parts. In general, what happens is that for every pairs of parts here, where G forms a superregular pair, maybe we don't have this edges here, we can consider the complete graph where we put in all of the edges across the parts where G is superregular. So that gives you some complete partite graph. And H is any bounded degree subgraph of these partite, complete partite graph, complete between parts, some parts. So that's the only constraint for H. And the guarantee is that this graph G always contains a copy of the graph H. Questions about the statement? The good place right below this statement. This is a classical result of Combinatorics and similarity, and it's a very powerful tool to prove the extremal combinatorics results that we have mentioned before. For us, we want the probabilistic generalization of this result. So that's what I will state here in parallel with this theorem. The random blow-up lemma or the spread blow-up lemma. So the statement will mirror much of what happens there. So let me really maybe, I need one definition first. Say that a probability distribution lambda on a bunch of mappings, homomorphisms, embeddings, regardless of what you want to think about it, between two domains, X and Y. Usually we'll think about this as an embedding of the vertex set of some graph H into the vertex set of some other graph G. So given a probability distribution over embedding, we'll say that this is P vertex spread if it holds that for all choices of pairs of elements x1, y1 up to xt, yt, the probability, if we sample some random embedding phi according to this distribution, that phi map xi to yi for all I across t, this decays like p to the t. Okay, so because we usually think about graph embedding, and this is kind of spreadness at the level of the vertex set. So this is why we call this the p vertex spread property. So now we can state the random blow-up lemma, which for maybe let me move here. So we'll see later that it's usually very easy to connect the vertex spreadness property to the corresponding edge spreadness property, which is what we want if we want to apply the Kahn-Kalai conjecture. Because if you remember, all of our random graphs, the random variable are on the edges, not the vertices. So we'll need to do a step that translates the vertex spreadness into the edge spreadness. But usually that's an easy calculation that we'll see in the specific application later. So, okay, so let me state the random blow-up lemma. And it builds on several ideas that have already circulated around. So maybe already kind of hinted in this work that I have with Sarasane and Simkin, but we wrote this down explicitly recently. So this is one explicit place where one can find explicit version. So random blow-up lemma has pretty much the same setup over there. There will be some more parameters, but we'll add them later as we need. Okay. So we copy some of the information from over there. So let R be a graph on R vertices. Let G be again apartheid with vertex parts V1 up to VR. And whenever I is adjacent to J in the graph R, the graph G between Vi and Vj is S1 delta, super regular. Again, they have the same information for H. So H is a graph with this homomorphism from H to the graph R, and the inverse image of each part, each vertex in R has size exactly equal to N. Oh, did I? Yeah, it's exactly equal to Vi. Actually, in all of the cases, let's always make this assumption, which we can in most cases, that all of the vertex parts are equal and they are equal to N. And of course, the important condition is that H has value degree. Okay, so the conclusion is that there exists a probability distribution lambda on embeddings from the graph H into the graph G that is big O, depending on all of the parameters, 1 over N spread, when this is optimal of vertex spread. So when we use the regularity method, because of the somewhat annoying exceptional vertices and so on, usually we cannot just apply the vanilla blow-up lemma. This is intuitively what we apply in a majority of the vertices in the graph. But then because of a small set of exceptional vertices, we need to make a bit of a generalization of this statement here. But if you prefer, you can just ignore this additional technicality. So we'll have two additional parameters, alpha and beta. Then we have some additional information here. So we will have some vertex subset W of H. It should have size at most beta n. And it comes with the following information for each X in W. It has a desired target set. Okay, so we are given this set Wx, which sits inside the corresponding part V of H of X. And we assume that this Wx will have size at least alpha n. Then we can still have exactly the same conclusion, just with the additional property that this is not only just an embedding from H to G, but it's an embedding from H to G such that the image of X is in Wx for all X in this subset W. But if you prefer, you can just ignore everything in red. Any question about the statement?
Over N is is there any explanation of this growth?
Right, because Well, we only have n vertices. So for each vertex of H, we only have, well, we have some constant times n many vertices in G, but for each vertex of H, its potential set of destination will have size at most n. Okay, so if we have a distribution, because there are only n options, of course, some option will be taken with probability at least 1 over n. Right, so we see even if we have just a single pair, we cannot put something better than 1 over n. And so yeah, that's right. Okay, so right, so the regularity method in the plot lemma has lots of applications. So ideally, if one looks closely enough, then this version should allow us to bring many, and most probably most of these applications to this probabilistic robust threshold generalization of the extremal combinatorics results. Okay. So with the small amount of time that I have left, I will tell you at least maybe just a little bit about what goes behind the proof of this random flow lemma. Let's say really the main insights, the heavy lifting is belonging to this work of Combinatorics, Sarkozy, and Semeredi, where they already write a very nice proof of the blow-up lemma, and we can observe that with some additional ideas, we can push it to this random version. Okay, so maybe I just say here some ideas. It turns out that the key tool, this I will prove to you in detail tomorrow, is the following lemma. So this lemma is a lot cleaner. It's just saying that if we have G bipartite graph that is epsilon delta superregular, then there is a distribution lambda over perfect matchings of G. That is optimally spread. So this is really the core driving the spreadness, vertex spreadness of this distribution lambda of embedding. And I'll tell you maybe just a little bit after this, at least this main scheme for the proof of Combinatorics, Sarkozy, and Semeredi. They have an algorithmic proof of the blow-up lemma. So they have a procedure where they embed the vertices one by one. Most of them are embedded randomly, so that comes naturally with the spread property. And then the non-trivial step is at the end of the embedding procedure, where they apply Hall's theorem in order to find some perfect matching that closes up the embedding. And all that we need to do to bring it to the random version here is to replace the application of Hall's theorem by this spread perfect matching lemma. And somehow, coincidentally, maybe I can tell you just a bit tomorrow, there are also many other works recently along the same direction, and many of them are regularity free. So they produce the robust analog of the Dirac type extremal results for many type of structures without using the regularity method or the blow-up lemma. But in many of these cases, it also turns out that the key tool that one needs to run the proof is the same lemma about perfect matchings in bipartite graph. So that's one of the reasons, at least I feel like tomorrow I will give you the short proof of this key tool here. And now for the rest of the time, maybe I'll just quickly give you some brief overview of how the blow-up lemma is proved. It's in the extremal setting, and at least convince you that you can push that proof to this random setting. So So what happens in the proof of the blow-up or the random blow-up lemma is we will try to keep a partial embedding of H. We embed one vertex of H at a time, and then we try to keep the embedding so that it has some nice quasi-random property. So enough time for this. So what's a quasi-random embedding for us? Well, okay, so first let me set up some notation. So let's let Hi be just the vertices of H that sits in the ith vertex part, right? And so what we do first is we pick arbitrarily Bi and Di in the ith vertex part of H so that they have, well, first the right size. So the size of Bi is delta naught n, and the size of Bi is beta n. Okay, really, once we are here to ignore all of the small constants, they are chosen. I guarantee you that there's an appropriate order in which the small constants can be chosen so that everything fits together. But let's not keep track closely of how the constants are behaving. And we will guarantee that B union B, which is really the union over all I of Bi union Di, every pair of vertices from here in B union B will need to have distance at least 4 in the graph H. And because H has bounded degree, this you can easily do. Okay. So now I'll define this quasi-random property for the embedding. So given a vertex subset S of H, think about these are the vertices of H that we have embedded. We say that an embedding phi from S to the graph G, right? This way better. So H on the vertex at H, S to the graph G is quasi-random if the following holds. So for every vertex X that we have not yet embedded, let's define the following set. So we embed the vertices of H one by one. Now, for the vertices that have been embedded, they will give us some constraint, right, for the future vertices that we want to embed. For example, if we have a neighbor of a vertex that have been embedded, we need to make sure that the neighbor embeds into the corresponding neighborhood of that vertex in G. So that is why we will define this set, which just keeps track of all of the potential options for this unembedded vertex X after phi has been fixed. So this will simply be, okay, so let me write this notation first. Let's maybe ignore the W for the sketch. Let's ignore the W. So V of H of X, this is the vertex part where X is supposed to go to. Then we intersect it with the intersection over all of the neighbors of X that have been embedded. And here, we will have to then embed the vertex X into the neighbor in G of the image Phi of Y. So this is our feasible set. And we first want this feasible set to be large in order for phi to be quasi-random. So we want the size of Cp of X to be at least B minus epsilon to the number of already embedded neighbors times n. So let me make one remark. I already used this lemma that I proved before. So without loss of generality, I can assume that these graph G, B, I, B, J, they all have the same density, that's D over there, and they are all epsilon superregular. Okay, so now everything have the same density, everything is just D. And there's a small technical condition, which maybe I'll just write down. So for each I, there are at most some small epsilon prime times S times N, many pairs XY, both of them belong to this ith vertex part of H. Okay, there's a bit of a technical part here which you can ignore. And for almost all pairs, their feasible sets will need to have a large intersection. And large means the right number up to this plus epsilon. So classical study of quasi-random graph will tell us that if we have these types of co-neighbor, co-neighborhood control, then we can force a graph to be quasi-random. And that's indeed one of the main input that we will need. So let's say briefly how it works, and then I'll just describe the output. So given this partial embedding phi, we can construct the following bipartite graph. So given some vertex set U, so think about here, U is a large subset of vertices of H that we want to embed into this part VI. Okay, because of the embedding phi already giving us some constraints, for every vertex U here and V here, well, okay, we will put an edge between U and V if V belongs to C phi of U. So V is one of the options for U. Okay, so this graph will be very important for us. It tells us where we can embed the vertices from H into the graph G, and roughly matchings in this type of bipartite graph will be exactly what we want to find in order to get the embedding that we want. So here we'll define this bipartite graph to be what we call BI of C and U. So U here sits in HI. So the condition is that in most cases, this bipartite graph that we construct will be quasi-random, will be epsilon regular for some epsilon. So the condition is that if you stay away from this dangerous set D, U is large, and the neighborhood of every vertex in U intersected with the embedded vertices in S have the same size L, then this graph, bipartite graph, is regular with density roughly D to the L, which is the correct number. So
Is the W where S?
yes. Right, W is S. Okay, so with that, I will not have a lot of time to tell you how all of the elements in the proof will play out. Just tell you how we embed the graph H into G. So what we do is, what Combinatorics cycles is already do is they take first an ordering. So first you order the vertices of H. And in this ordering, you want the vertices in B to come last. They are kind of the easiest guys to embed anyway. So we push them to the last of the ordering, and we will embed all of these vertices by finding a spread perfect matching. All of the vertices in the neighborhood of B will come first. So we'll first try to embed all of their neighbors. Okay, so that's first the only rule that we have. Then we embed vertices one by one. So as we do this embedding, we will try to maintain that our embedding is quasi-random in the sense that we write down here for every step of the procedure. So at step J, so we have embedded J vertices. We will define AJ plus 1. This will be the subset of the feasible vertices for the vertex xj plus 1. And we cannot reuse a vertex that we have embedded. So here, okay, so the vertices are x1, x2, dot, and I'll let xj be the initial segment. So we define this set AJ plus 1. It is exactly the set of vertices V in this feasible set for xj plus 1, so that extending the embedding to V gives you the quasi-random embedding. And once we define this, we will just pick the image C of xj plus 1 to be in AJ plus 1 uniformly at random. So as long as the set AJ plus 1 is large, picking uniformly at random will allow us to still automatically guarantee the spread property. That's why we want to do things in a maximally random way. Now, you can actually show that with this procedure, you can always succeed and obtain a quasi-random embedding until after you have embedded all of the vertices in the neighborhood of the set B. So, okay, what's the role of D? There will now be a special step. And that is important for the end of the process. So in this special step, we take, so for J being now NH of B, so we have embedded everything in the neighborhood of B. We'll let EI be a dangerous set of vertices. So now these are vertices of G such that there are few vertices of B that puts B in its feasible set. Okay, so the vertices that are the options for too few of the B, we throw out to this dangerous set EI, and now we use the set DI to embed these guys. So embed DI into EI at random. Okay, there's one small thing. So we also. Okay, so after this step, let's let T be the set of embedded vertices. We'll need to follow it with a few iterations of this type. We just continue like the usual step. Continue like usual, except for some special mark step, unless J is a multiple of some parameter s. S will be again like of order n. Then in every one of these special steps, we take a look at all of the vertices that have potentially too small a feasible set, because we have now embedded many things. We may start seeing vertices with a small feasible set. So small means less than delta 1n. And we move all of them to top of the ordering. So we will try to embed them next because they are dangerous. And then we can show that we can still always guarantee that once we move them to the top of the ordering, we can embed them. So now after this step, we are done with the last step. So after this, in phase 2, we will only have left the vertices in our buffer set B that we separate and put to the last of the ordering. So in phase 2, we will construct this bipartite graph between the unembedded vertices in B and the potential places that they can go to in X. So here again, you just connect a vertex here with a vertex here if X is a choice for B and it has been induced by other vertices. So you check that this is superregular bipartite graph. So you can then find a spread perfect matching. And this perfect matching will now complete the embedding that has the claimed optimal spread property. Okay, so the algorithm is somewhat complicated, has a few steps. So can take questions now. Can tell you more about any steps that bothers you.
That's okay. Now from this special step, that was a little bit fast. So
Yeah.
J is the number of neighbors of all B.
So here, right. So what I mean here is just once you have, so I guarantee that nothing goes wrong until you actually embed all of the neighbors of B. Anyway, they come first. So we will embed them first.
We finish them.
So we finish them. And now at this step, when we finish them, which is exactly the step with number NH of B, right? Because we have already embedded all of the neighbors of B, we will stop and we look at these special vertices in G.
In G.
Right. So in G, each vertex may be the potential option in the future for some subset of the vertices in B.
Right.
If they are belonging to too few of these potential sets, then we separate them out into this set EI. We only want to keep the guys that will be useful for many Bs in the future. So we throw out those that are not very useful. And then we have already reserved this set DI in advance. So we will just embed DI into these destinations in EI.
We will make sure DI is larger than this EI, right?
Right. So EI will have to be small. We guarantee that by regularity.
So we're filling, get rid of those bad vertices EI.
Yeah.
Now capital T is the currently embedded vertices.
Yeah. So maybe T will be pulled down here. So forget about T for a second. So let's just think about what we continue after the special step.
So what is the continue part? We continue.
So after the special step, we will continue just like what we do here. So next vertex, check the feasible set, check what will be an option for us, and put one option uniformly at random.
You do
But
whatever vertices that are not in B, right?
So now these are vertices that are not in B or the neighborhood of B, potentially. These are just vertices, remaining vertices, right? And once we hit the remaining vertices, the only tricky thing that we need to do is every delta 2 times n many steps. So whenever the index is a multiple of this parameter, we will stop. We will look at all of the vertices that have potentially too small a feasible set.
So XJ, what's XJ?
So Xj are the set of vertices
Neighbors.
from in the first J vertices in the embedding. Yeah, so they are just the first J vertices in the embedding. We're not constraining anything about the neighbor here. So these are just the vertices that have been used by the embedding of the first J steps, right? We cannot reuse them, so we throw them away. And these are the feasible vertices that we can use to embed the vertex B into. So in total, this is the feasible set. At this stage, because we have continued for a very long time, this feasible set, even under the quasi-random condition, this can be small. This can be small.
So LJ is the vertices in H that are sort of hard to embed now.
Right.
As the feasible set gets smaller.
That's right. So yeah, so Xj are the vertices in H that have been embedded. Now for the rest of the vertices that haven't been embedded, so they are in H. We are looking at those for which they have too few options.
I see. So at every little checkpoint,
Right.
you check which one are dangerous, then you move them
Pull
to
them
higher
to the
priority,
beginning. Yeah,
priority and then do them,
right,
and then repeat.
right. So yeah, that's one thing that we need to do in order to guarantee that things will run. So after we run this all the way to the end, so all the way until, so we will run this until we have only vertices in B that haven't been embedded. But some of the vertices in B may have been pulled forward, so they have been embedded. So we only have subsets of B that are not embedded at this point. So I'll let T be.
Phase two only starts when vertices outside of B
Have all embedded.
Okay.
Right. So phase two only starts to embed the remaining vertices in B.
Okay.
So T, I denote the vertices that have been embedded before phase two. And now we have the vertices that are not embedded yet in B. We have the options that are not used yet in the previous step. We construct this bipartite graph, which tells us what can go from B to like which pairs are feasible for the embedding. And then with the perfect matching here would exactly mean one way to finish the embedding.
I see.
So, right, let me note also that there are other proofs of the flow lemma, but still one common thing is all of them at some point would use some result that guarantees a perfect matching. So you can still then try to use the same tool for finding a spread perfect matching in order to get in via other means spread flow lemma. But somehow this spread perfect matching is fairly universal. It's pretty good.